Hello, everyone. Um, Today we're going to cover the chi-square. If you look at the syllabi, it says that we should be covering the chi-square on December. I decided to actually provide you with this lecture a little bit earlier, simply because this is a test that I think a lot of you gonna end up using for your final project. This way, you kind of like a little bit more familiar. Although you're gonna be using a SPSS, nevertheless, it's a good idea to understand what the test is all about before you start writing about something that you're not even aware of what it is. All right. So what are we going to cover today is, as I said to you, we're going to talk about chi-square, when to use it, and also we're going to cover the very basic steps of how to compute using SPSS. I'm going to show you my favorite way of computing SPSS, I mean computing chi-square using SPSS, although there's another way. Um, but again, I think for the purpose of your final project, I think the way I'm going to show you is probably the best way to do it. Okay? So far, what have we done? We have compared one sample to the population. And do you remember what test we do for that? So remember, we're having one sample and we are comparing that to the population mean. That is going to be a one sample z-test statistics, okay? All right, how about this one? Two groups and you're comparing them on a dependent variable. What kind of test is that? This is what we recently covered, so that is going to be a t-test, remember? All right. And I saw a few of you in your homework, you used actually the formula in the book to calculate the t-test. Please be aware that on your final test, if you're going to see a t-test statistics, it is used with the formula that I'm giving you in the PowerPoints, okay? So make sure if in case I'm giving you a multiple choice options and you're solving it and you're not getting exactly what you're supposed to be getting, it's because probably you're using the wrong formula. So please look at my PowerPoint, which should be x bar 1 minus x bar 2 over the pooled standard deviation, okay? So the dependent variable is primarily scale so far, right? So we had some kind of a numerical continuous type of variable, real numbers. So the thing is, well, as the comic book bikes are here, what are we going to do if we actually have two categorical variables, right? So if we're having two variables such as gender, hair color, eye color, even ordinal values that they're organized in categories. What do we do with those? Well, hold on, we have a very special test for that, and that's going to be the chi-square. So chi-square is a test that we use to actually analyze anytime that we are dealing with non-parametric measures, specifically when we want to find associations between categorical variables. So and this is how it looks. So try to imagine you're looking at obesity, right? So you're either obese or you're not, okay? And gender. Now, of course, keep in mind that there is a way that you can turn obesity into a numerical if you're looking at BMI. So maybe you're looking at the BMI numbers and then you're going to have continuous like 30, 31, 32, 33 BMI. That would be a whole different animal to analyze. But now we're going to assume that you have a survey and it has just an option of are you obese based on some kind of criteria, yes or no. So apparently it would be anybody who is above a BMI of 30, yes. Anybody who is less than a BMI of 30 would be a no. And then gender, and maybe we want to see if there's any association between gender and obesity, okay? So as SpongeBob says here, his is a square, and it is a square, okay? But this square that you're going to see here, we actually call it the cross-tabulation table, okay? So this is the proper name. So this is the cross-tab table. Now, when do you see a real-life example using chi-square? Many, many applications. Here, for example, we're having a scenario of the number of physicians in practice, right? How large a practice is, and the utilization of electronic medical records. So, could you tell me which one is your IV and which one is your DV here? Remember, your IV is always going to be in the x-axis, and your DV, the outcome, right? It's going to always be your y. So the number of physicians in practice is going to be your independent variable, and the utilization of electronic medical records, that would be on your y-axis. So pretty much what we're trying to say here is uh, depending on how large a practice is, the more likely they're going to be utilizing, the greater the percentage of physicians that they will be utilizing electronic medical records. And of course, that makes sense. So in this particular case, it is some kind of a positive association between physicians, okay, and how large a practice is and if they're going to utilize electronic medical records or not. Now, as I said here, I use the word association, not to be confused with the Pearson's R, because we talked for associations there as well. But remember, you only using Pearson's R when you are comparing interval or ratio type of data. Okay, so the level of measurement of your variables, it has to be a continuous number. Okay, it cannot be categorical. Chi-square is the one that we're going to use when we're actually having categories. And something else, you can use chi-square even if you have more than two categories. You can have several categories and you can still use chi-square. In Pearson's R, you can only have two, okay? So you can only correlate two variables. So be aware of these little differences, and that's the idea. Every week we're going to be covering a new test, and it is your job to differentiate between the different tests and realize what you need to use for your final project. This is where I'm going to evaluate to see if you actually understand your lectures or not. Okay? So, a chi-square, how do we form the null hypothesis? Okay, so a null hypothesis would look something like there's no significant differences between observed and expected frequencies, and I will explain what observed and expected frequencies are. An alternative hypothesis would be there is a significant differences between the observed and the expected frequencies. And if you want to write it using notation, that will look HO, that is going to be your null, right? So P1 equals to P2 equals to P3. So those are the number of categories you're having, right? So parameter 1 equals to parameter 2 equals to parameter 3. And your alternative, which says that there's differences between the three parameters, okay? This is your formula. This is what you're going to use. You're going to see on your very last homework, you're going to have to calculate a chi-square manually. So let's take it apart. So the chi here, this is actually a Greek letter chi, and in English you pronounce it a chi with a square, not chi, chi, equal to the summation of this large sigma. And I want you to notice that the sigma here is in front of the whole fraction. That means it applies for the numerator and for the denominator. Parenthesis here, the observed minus the expected value square over the expected. Okay, there's nothing more. There's not it's a very easy formula to follow. And let's go ahead and do an example. Okay, so as it says here, let's just assume that we're having a coin and we flip the coin 50 times. Normally, in a perfect world, right, you should be getting an even amount of heads and tails, right? You should be flipping 50 times. That means you should be getting 25 heads and 25 tails. But in reality, though, that is not what you're going to get. Otherwise, but I mean, if you keep flipping though that coin, eventually you should be reaching an even amount, because it's not like the one side is better than the other. And assuming that you're not tossing the coin a special way, so it flips always in one side, or the coin is not more heavy in one side or not. So anyhow, so you just flip it this time for 50 times, and what you end up getting is 28 heads and 22 tails, okay? So the 28 heads and 22 tails, this is your observed values, not your expected. Your expected is what you would expect in a perfect world, but not what you actually end up getting. What you end up getting is going to be your observed values. Now, in order to form our null hypothesis and our research hypothesis, it's going to look something. The probability of heads should equal, right, the probability of getting equal tails. So there's no difference between the heads and the tails group. And the alternative should be that they're actually not equal. Now, the degrees of freedom for this particular test, right, is the number of outcomes and we take away one. So in this particular case, the possible outcomes would be the heads or tails minus 1, so degrees of freedom would be 1. Alpha level, we're going to stick with 0.05. And if you go to the chi table now on the back of your book, I will also make it available online, it's going to be a 3.8. And this is how you would solve it. I just made a copy and scanned the paper. I solved it manually and I put that on the slide. Sorry for the bad handwriting. So anyhow, I created a little table here that separates of what I'm supposed to be getting, the expected and the observed values. So remember, we flipped a total of 50 times. So if I would add this, 25 plus 25 is 50. And in the perfect world, as we said, we would expect to get 25 heads and 25 tails. Unfortunately, though, right, after we flip the coin for 50 times, we end up getting 28 heads and 22 tails. The question is this difference from what we were expecting to get and what we end up getting significant enough to say that there's a major difference between getting heads and tails, right? So this is our formula again, the chi-square equal to the summation of observed minus expected squared over expected. And I'm having it right here. And this is how it's going to go. Remember here we're having two outcomes, heads or tails. So the reason of this big sigma here, the summation, is that we're going to have to do it one time for the heads and one time for the tails. Okay, and we're going to sum it up. Okay, so it's going to be the observed, which is 28, minus the expected for the heads, right, squared over the expected, plus 22, which is the observed for the tail, minus 25, which is the expected for the tail, squared over 25. We do the math here and we end up getting 0.72. We said before that our critical value was 3.81, which is way greater than 0.72, okay, which means we fail to reject the null because this value here, our test statistic value, is not greater than our critical value. So we gonna stick with a null for now, okay? So there's nothing wrong with a coin, okay? There's no significant differences between heads and tails. Now I want you to pay attention to one thing. You see how the chi value is squared? Which means what? You will always be getting a positive result since it's a squared value, which means you're never going to be running any kind of test that runs on the negative tail, okay? So if you look actually at the very beginning of my slide and also if you look on the chi table, you're going to see that all your critical values are centered on the right side of the curve simply because this is a squared value test. Okay, so you would always be having positive values. So you don't have to worry here about being a one-tailed test or a two-tailed test. This is not something you need to worry about the chi-square. Now let's look at a little bit more complicated example. So here you're going to have occupation and pet preference. So what is the association between someone's profession and the kind of pet they like? Okay, so apparently here we have 100 total people and we went out and we asked them, so what do you do for a living? So 38 out of the 100 people were teachers. 32 out of the 100 sample size were salespeople and 30 were farmers. Now we went ahead and we asked the teachers between, do they like cats, dogs, or something else? 26 teachers like cats, 10 teachers like dogs, and 2 of them liked something else. Out of the salespeople, 10 like cats, 18 like dogs, and 4 like something else. Farmers, it was an even split. They liked it all evenly. Okay? So this is how you read the table. Now, if we were to say like how many people out of the whole thing like cats, you would add them up this way. So 26 plus 10, 36, 46. So 46 out of 100 is going to be the cat lovers, right? Likewise, 48 here would be the dog lovers, and 16 out of 100 would be liking other pets. So the research question for the example given to you is like, is there an association between occupation and pet preference? So you would form a null hypothesis that would state something like there's no association between occupation and pet preference. And the alternative hypothesis would state something like there is an association between occupation and pet preference. All right. So normally, the way you would do to calculate the expected values, it would be a very painful, lengthy process, okay? Because you would have to calculate the expected frequency for everything. Because imagine you're not going to be having the expected frequency. So what you would normally end up doing, you would be calculating the frequency for the teachers, and then you would calculate the frequency for the cat people, and then you would multiply the two, and it would be just a big pain in the neck to do for everything. And then you would cross multiply the two in order to be able to find, the total percent of people who happen to be teachers and are cat lovers as well. And you would do this for every single cell, okay? So you do not have to do that, okay? So for the word problem that I'm giving you on the homework that you're going to see, your last homework, you're going to follow the example that I gave you right here, okay? So this is how you're going to calculate it. Now for more complex examples, okay, we are actually going to use SPSS, which is way, way easier. And the only thing that you have to do is just simply click and then read the output. Yay. All right. So how do we do it? All right. So we're going to go to your favorite menu. As we said, Analyze menu is going to be your best friend. And as SpongeBob says, hold on, there's no square, chi-square here. No, it is not. So you're going to go actually under descriptive statistics, and in there you're going to find something that's called crosstabs. You're going to click that, and it's like crosstabs. Yes, it's from the cross tabulation table. And what you're going to do is you're going to put your two variables in the rows and the columns box. It doesn't matter which one you put in the rows and columns. Just simply place any variable on the rows and it's the same thing because you're cross tabulating, so it really makes no difference. Then the next thing that you have to do is click on the statistics button, and what will happen is it will pop up in another box, and there you need to make sure that you're going to click the chi-square here, the phi Kramers V, okay? And you're going to click OK, and then you're going to click the cells button. On the cells button, you want to make sure that the observed values are checked, the row, the column, and the total. After that, you're going to click OK, and this is what you're going to be getting. It's going to be looking like a very large table like that, okay? And as you can see here, you have your cross tabulation table, which is in your final project. You should copy paste this one, and also this one right here, and this one. So this is what gave you your chi-square test, and this is your phi Kramers V test, okay? All right, so let's go ahead and see what it says, this cross tabulation table here. So what it's telling you is that you have apparently within the teacher occupation, you have 26 of them like cats, as we said before, 10 like dogs, and 2 other. But here though, it actually starts calculating all the percentages for you, which is kind of great. Now, this total here reflects the total number of teachers. Okay, so right here, this is 38 teachers. The 68.4%, that is the percentage, as it says here, which is within the occupation. So within all the people who are teachers, 68.4% like cats. Within the pet preference, that means within the total number of people who like cats, 56.5% are teachers. Okay? You do not worry about the total here. Likewise here, you're going to have the salespeople, and this is within the occupation. So out of all the salespeople, which are 32, 31.2% of them, right, likes cats. 56.2% of salespeople like dogs, and 12.5% of salespeople like other. This is within the pet preference again, okay? So you keep going the same way. So out of all the people who like cats, 21.7% are salespeople. Out of all the people who like dogs, 47.4% are salespeople. And out of all the people who like other pets, 25% are salespeople. So this is how you read between the various percentages. Now, in your final project, I don't care about if you're going to use the within the occupation or within the pet preference. Use whatever makes sense to you, but stay consistent. Okay, so if you're going to state something here within the occupation, for example, you should be doing this with all of them. Okay, so that's what it matters. Alrighty, so we just covered that. Now let's go see what you need to read here. So this is the chi-square table. Make sure you also copy paste this table. And here's your Pearson's chi-square value, okay? So this is your actual value. This is your degrees of freedom, okay? And this is your significant level. So here is telling you that the significant level is 0.001. Well, guess what? 0.001 is less than 0.05, which means we got significant results. So there are significant differences between occupation, right, and pet preference. That's what this is telling you. Now you're looking again at the Phi-Kremers V, which is a type of after the fact test, post hoc test. We're going to cover a little bit more about those. But you also want to see the significance on that. So the Phi-Kremers V here is telling you that it's at also at the significant level of 0.001. So this is great. Okay, as it says here, we're not assuming the null hypothesis. So that means you got significant results. And you are done. So this is chi-square for you. And hopefully, I know that you're also having test 2 this week. I just wanted to introduce it a little bit early, so spend some time familiarizing yourself because once again, you will see that on the final project, quite a few of the variables are nominal or ordinal, so this would be a good test for you to use. All right, have a good one. Bye-bye.